So what's the secret behind implementing a stack that lets you get the minimum value in constant time? Imagine we have a normal implementation of a stack data structure. You go ahead, push some values onto it, and then you're asked to get the minimum value. This time it's easy because -2 is right there. But now, what if we pop -2 and ask to get the minimum value again? How do you get 5 in constant time? So this is where a second stack comes into play. The sole purpose of the stack is to store minimum values. If the second stack is empty, push the element onto it and push it onto the first stack. If the second stack is not empty, you have to compare it with the top value and make sure it's less than to push it on. In this case, since a is greater than 5, we only push it onto the first stack. Since -2 is less than 5, it can go onto the second stack. As usual, we always push values onto the first stack. Now, we check for the minimum value, and all we gotta do is return the top of the second stack. When popping, we only pop from stack 2 if its value is equivalent to the top of stack 1, which it is. When checking the top, you just check the top of stack 1, and when you're getting the min, as usual, you just return the top of stack 2. So that's how you solve minimum stack. The space complexity is O of n because we are using another data structure to store these additional elements, and the time complexity of each function and operation is constant. The common gotchas are the following. Just make sure when you're pushing or popping from the second stack, you're doing the rightful checks and ensuring that that value should actually be pushed or popped from it.